Calculus 3 tutorial, we will see how to evaluate the limit of this multivariable function as xy approaching 0, 0. So first, we should plug in 0 into x, 0 into y. But if we do that, we get 0 over 0, so we cannot draw any conclusions. Next, maybe you should try it along some path. So if we do it with the path x equal to 0, and we keep the y, on the top we get 0, on the bottom we get y squared, that gives you 0. And if we do it along the path y equals 0, and we keep the x, we get 0 over 2x squared, that will also give you 0. But we cannot draw any conclusion that the limit is indeed equal to 0 based on these two paths. Because when we want to evaluate the limit of a multivariable function, it's kind of hard. But I do have a video for you guys showing you guys all the ways that you should know for doing such a thing. Make sure you guys go check that out. The link will be in the description. For this one in particular, let's try to do it with the squeeze theorem. And you might be wondering, why don't we try the polar coordinates? Well, one reason is because we have a 2 here, so the bottom does not simplify that well. And also, the other reason is, if you do polar coordinates for this, you still have to do some kind of boundary work, which is kind of like squeeze theorem as well. So we might as well just do squeeze theorem with x and y. So let's go ahead and make some observations, because we need to have some boundaries for the function. So first, let's look at x squared y cubed over 2x squared plus y squared. Right here, let's go ahead and apply the absolute value. This way we can see this is never going to be negative. And now because we have this is greater than or equal to 0, so hopefully later on we can also show this thing is less than or equal to something that approaches 0. Then we can use the squeeze theorem and argue that this thing here will be approaching 0 as well. Let's just do some algebra. The absolute value of a quotient is a quotient of the absolute value, meaning we can do the absolute value here and here. For the top, the absolute value of a product is the product of the absolute value. Let me put them down first. Absolute value of x squared is just x squared because this is never negative. And then we need the absolute value for the y cubed. And then let's put on the denominator like this. We don't need the absolute value here because this is never negative either. So what do we do next? This is kind of bad because if x, y approaching 0 and 0, we get 1 over 0. When we do limits, we get some kind of infinity. No. So how can we continue? The key right here is that we have x squared and also y squared. On the top, I also want to have some kind of square, either x squared or y squared, so that we can set up a boundary very nicely. Hey, we do have x squared right here, right? Why don't we bring this up here and then use that? So let's go ahead and make that work. So I'm going to put down absolute value of y cubed times x squared over 2x squared plus y squared. And now we are in business because this part has a very nice bound. What is it? The answer is 1/2. And the reason is because on the bottom we are just adding y squared, and then this and that are never negative. So this is very nice. We can say that is less than or equal to 1/2. When you ignore the y squared, this thing right here is smaller than equal to, I will write this down. This is smaller than or equal to x squared over 2x squared. And then you can reduce that and just get 1/2. So that's how we end up with the 1/2. Thanks to that. Yeah, and then none of this is going to be negative, so we have no worries at all. And then right here we have y cubed in the absolute value. This is great because as y goes to 0, this will also give you 0. So now, once we have this right here, we can say the absolute value of our function it's in between of this and that. So we just have to take the limit as x, y approach 0, 0. This right here will give you 0, and this right here will also give you 0. And in the middle, we get the limit as xy approaching 0, 0. And let me write this down. Okay, now you see that this thing right here, it has to be equal to 0 as well. And the reason for that is because of the squeeze theorem. So based on this, we can actually conclude that the limit of the function that we're looking for as xy approaching 0, 0, this right here has to be equal to 0 as well. And that will do it.